Hello pre-calc students. Today we're going to talk about what power functions are. Power functions are, first of all, they're the simplest kind of polynomial functions, just like a monomial is the simplest of all polynomials. It's one term that makes up, you have more terms and you have a more complicated polynomial. So a power function is just a monomial function. In other words, f of x is just a single term. There's nothing being added or subtracted. So f of x is just a single term. We're going to write it as a times x to the k. Now these are just commonly used variables here, but they're not the only ones that are used for this kind of discussion. But a in this case can be any real number. X is our independent variable, can also be any real number. And then k is considered to be an integer in this case, just to make these power functions. Okay, so not only an integer, but a positive integer. So I'm going to just write those requirements down. Okay, so there's our general form for a power function. K is any integer greater than or equal to 0, but it's really not going to be very interesting if k is 0, because then you're just going to have a 1 here. Right? Anything to the 0 power is 1. It's also not going to be very interesting if k is 1, because then you're just going to have x to the first power, which is just x. That's just a linear equation. What this lesson is really about is when k is greater than 1. And it's an integer greater than 1. So we're talking about 2, 3, 4, 5, 6. We're going to separate these out into the even exponents and the odd exponents. And then we're going to get our even power functions and our odd power functions. So some examples of power functions would be f of x equals 3x. That would be an example. G of x equals negative 5x squared. That would be an example. H of x equals 8x to the third. That would be another example. So I'm just going to write down a couple of examples. Okay, so these are all just examples of power functions. And as you can see, a line is an example of a power function, and so is a parabola. This is just a parabola. And so is a cubic. And it goes on, though, because k can be any integer greater than or equal to 0. Now, this is a little activity that you can do this on your calculator screen, or you can do this on Desmos. But I'd like you to take a look at it, and then I'm going to show you, and we're going to discuss it a little bit. Okay, so what I have here is I have a graphing calculator that I've put the 3 equations in. These are just unaffected. These are going to actually be parent functions. They're not affected by any transformations. In other words, they're not moved or stretched or anything like that. No reflections. And we're just going to first look at the window. I'm going to set the window in a way that you can kind of see what's happening a little bit better. So copy this window. It just goes from -2 to 2, increments of 0.5 in both x and y. And then let's take a look at our parabola. Okay, we already know what to expect. We know it's a parabola. We know the general shape. What's important here is that this point is 1. And then over here is up 1. So this is the point 1, 1. Keep an eye on that point, okay? And then also this is -1, 1 right here. Keep an eye on that point. Now we're going to add on x to the 4th. Let's see what happens. Just get it highlighted. All right. Now notice that those points that I pointed out, the 1, 1, they're still there. And think about the equation. I'm sorry about the coloring here. I just can't really seem to get it right. It's either a glare or it's yellow. So if you think about it, if you plug in a 1 here, you're going to get 1 as the output. So we expect those outputs. But everything else is different except for, well, 0, -1, and 1. Those are the only things that remain the same. Let's try this with the 6th power. And we kind of know what to expect. It's going to have that point again. But let's just take a look at what that looks like. Can hardly even tell the difference. But what's actually happening here is those points remain the same, the 0, 1, and the -1. And that's kind of nice because they really all kind of resemble parabolas. The only thing that's different is that when you go past the 1, it goes up, each of these goes up more steeply than the last, the higher the power. And when you're between -1 and 1, it hugs the x-axis more closely than the standard parabola. Because remember that first one where you can see some space there, that first one is just y equals x squared. Okay, let's plot these. So the way I'm going to plot these is I'm going to make the same scale that we just made. So this very end of the graph that we have, these are 2's, -2 and +2. halfway, so right there, that's going to be our 1 and our negative 1 over here. All right, and then the same thing going up and down. So way up here is the 2, halfway is the 1, same thing going down, 1, 2, 3, 4, 5, that's negative 1, and 1, 2, 3, 4, 5, that's negative 2. That's not a 4, that's a 1. Okay, so now what we know is that all three of these graphs right here are all going to contain the point 0, 1, or 0, 0, 1, 1, and negative 1, 1. We know they're all going to have that. And I'm just going to graph the standard parabola in black, and I'm going to keep it not too close. I'm not going to make it, maybe you should just watch first before you plot these so that you can, whoops, I missed the point completely, didn't I? So that you can see the difference. So now I'm going to plot the x to the 4th. So this one is y equals x squared. Now I'm going to plot y equals x to the 4th. And the difference is, compared to x squared, it's going to come closer to the axis until it gets to that 1, 1. Then it's going to be a little bit steeper. So same thing going in the negative direction. Now you can go for it now that you kind of get that idea. Okay, so the red is y equals x to the 4th. Now let's plot one more, and that's going to be y equals x to the 6th. And this one's going to even be closer down here. So it's kind of even hugs the axis more. And then it goes up much more steeply, so it looks even really more like a U, like it's not even going out. But it's still going up, it's just much more slowly. So that's kind of the idea. If you can tell what's going on there, this green one is the highest degree. This is y equals x to the 6th. But what's most important here is not the differences, but the similarities. These all resemble parabolas, and they're all even power. So what we just did is we opened up the door to a whole new family of parabola-like graphs that are all parent functions that we can now manipulate them. We can do the same transformations we do on x to the 4th or x to the 6th as we do on x squared, and we won't really notice much of a difference when we're looking at the process because they all look like they're just parabolas that are moved around, and we're not going to worry too much about that hugging the axis in between and going up more steeply. We're just going to focus on the same 3 key points and the same general shape of the curve. Okay, let's do the same exploration with cubics. So let's put the 3 cubes in the calculator. Odd power functions. Let's first put the cube, then the 5th, then the 7th degree, all in the calculator. Okay, and we'll set it up with the same window. Actually, no, not the same window. This time, yeah, the same window. This time we want to use this negatives, but we have the negatives. So the same window as before. All right, so there's the same window, window right there, and we have our functions. And let's look at our cubic function. And this time let's take a look at this point right here, which is 1, 1, and then this point over here, which is -1, -1, because it's an odd function, right? Let's now look at what happens when we add the next one. So we're going to add to the 5th. Let's see what happens. Actually, the same exact thing happens. If I were to describe the difference, it's exactly the same. It hugs the axis more between -1 and 1, and it goes up, but in this case, it also goes down more steeply once you pass -1, 1. -1, -1. Okay, so it's the same thing for the 7th degree. If we just add that on, we're not going to see much of a difference in the general shape. We might be able to tell that it hugs more closely and goes up more steeply, but even with this window, it's hard to tell. Okay, so let's put that on our graph now. Okay, and there's our new family of parent odd functions. These are all similar to the cube function. They all pretty much do the same thing. They just go up more steeply or more slowly. So this is just trying to it almost looks linear, the y equals x cubed, but that's just trying to give room to put the 5th and the 7th in there so you can see that they go up more steeply once they pass the 1, and they go down more steeply once they get to that side of it. Okay, let's look at some transformations of these 2 functions. All right, so here is an even power function that's having a transformation acted on, just as if it were a parabola, and we're actually going to treat it almost exactly the same way as a parabola. So if this were a parabola, then we know that this +2 on the inside means that the parabola would be moving to the left 2 units, right? So left 2. And this minus 3 on the outside means the parabola would be moving down 3 units. So we're just going to do the same thing. Now it says here to use a scale of 5, so that means I'm going to just go like this. 1, 2, 3, 4, 5, like that. That's what that's trying to say. Just makes it a little bit easier to see what's going on. Same thing going up and down, every other one. All right, so we have a parabola that instead of having the vertex at 0, 0, it's going to be at negative 2, negative 3. Right there is our vertex. And we know that that is not stretched. There's nothing being multiplied by the x on the inside, nothing being multiplied by the y on the outside. So we don't have to do very much to really get the other points here. It's just going to go over 1 and up 1 there, over 1 and up 1 there. Now that's what this function, fourth degree, has in common with the parabola. What we know is that it's not quite as, like, it doesn't go out as much. We're not going to have to bother getting intercepts here, but we can tell here that there is a, well, if we set x equal to 0, we get 16 minus 3. We're not going to bother with that because it's probably off the chart anyway. So we're just going to make it a little bit steeper, just make it look like it's kind of a little bit steeper than normal, hugs the axis a little bit more because it's fourth degree. And I don't know if I accomplished that or not, but I do want to make it look a little bit steeper. And there you go. So that is all you need to do. Okay, you're basically just graphing a parabola, not much different. All right, let's try the same thing now, graphing something with a little bit more transformation on it. So this is going to be similar to a cubic because it's odd degree. That's really the new part here, but we just have to figure out how to graph this. So we're going to use our transformation rules for something like this because when there's just a little bit more going on, it just makes it easier to find those points. So I know that I've got this transformation rule that takes the inside, I want inversely related to x minus 1. So I'm going to use xy goes to the inverse of x minus 1, which is x plus 1. Oops, I didn't mean the parentheses there. And then the y is going to go to 1 half y minus 2. Okay. So x plus 1 and then 1 half y minus 2. All right, so I know I've got those 3 points, the 0, 0, the 1, 1, and this is an odd power function, so it's going to be the negative 1, negative 1. Those points are on the parent function, and so when we apply the rule here, we're going to get 1, and then 1 half of 0 minus 2 is negative 2. So there's my new pivot point. It's not really a vertex for this, but there's my pivot point. Let's make the same scale. And let's just plot the 1, negative 2 right there. There's the pivot point of that function. All right, let's see what happens to 1, 1. Well, that goes to 1 plus 1 is 2, and 1 half minus 2 is negative 1.5. So I've got another point at 2, and then negative 1.5 right there. And then negative 1, 1 hopefully will be symmetrical here. So we have negative 1 plus 1 is 0. And negative 1 half of negative 1 is negative 1 half. So that minus 2 is negative 2.5. Minus or negative 2.5. So we've got 0, negative 2.5 right there. And there's our function. It just goes something like this. Goes a little steeper if you can convey that, and if you can't, really don't have to worry about it. These are our 3 points. They either have to be written off to the side or they have to be written right on the points. And that's power functions. I hope you found this helpful. This opens up the door to a whole new family. It can go 7th, 9th, 11th, 13th power, a whole new family of possible functions. And then the even ones all look like parabolas. They just get a lot skinnier looking when they get tall. They go up faster when the even powers get to be higher even numbers. Okay?